All right, in section 3.2, we're going to be talking about how to apply the standard deviation. And I'm in the 3.2 Learn section. And these are the things we're going to be looking at. We're going to calculate the coefficient of variation. We're going to calculate mean, variance, and standard deviations of group. Actually, we're going to skip this one. We're not going to do that middle one for group. That's a little bit advanced and more than what we need. We will be using Empirical Rule and Chebyshev's theorem to describe data variability. Okay, so let's go ahead and jump into it. So they right off the bat show you an example of applying standard deviation. I will show you my examples. You are free to look at the ones provided in Hawks. One of the first things they show you is the coefficient of variation. So this is noteworthy. You will need this formula. Basically, the coefficient of variation is used to really help you compare two different sets of data. So normally when you're looking at comparison, you want to compare apples to apples. Well, now we can compare apples and oranges and get an accurate result. For example, let's say that someone took the SAT and someone took the SAT. Both of those tests, the SAT and the ACT, have different systems of scoring. And if we want to know who did better on one of those tests, it would be hard to compare because they have two different scoring systems. So using the coefficient of variation, we would be able to compare those two accurately and tell which one we did better on. So here's the formula. CV is the initials for coefficient of variation. If we're dealing with a population, then we use sigma for standard deviation divided by mu is the symbol for the mean times 100 to get a percentage. And then if we're dealing with a sample, it's the same thing. Standard deviation over the mean is just different symbols. S is for sample standard deviation, X bar is for sample mean, and you still multiply by 100. Okay, so here at the bottom is just telling you again what I was trying to state with the example that I talked about. The coefficient of variation allows us to compare the spread of data from two different sources. Okay, so and then you have an example up here if they're talking about that. So read through that, but we'll have a problem in Hawks, and I'll show you how to use that. Here's another example that they give, comparing spread. And they show you here that when you do the standard deviation, A has this percentage, B has this, and from this it says it's clear to see data B has a larger standard deviation relative to its own mean. So the comparison of coefficient of variation shows that there's more variability in data set B than A. And usually more variability is a bad thing. We want less variability. Like we want to be consistent. Okay, more variability says that you're inconsistent. Less variability says you're more consistent. And we want consistency here. So A would be the better choice if you're looking for less variability. Okay, so empirical rule. Here is the description. I do want to draw this out for you. So we're going to be talking about empirical rule. They may also say bell shape, okay, as you can see to the left. Whenever you're given that, okay, the empirical rule, or they tell you bell shape, okay, all of the following is true. So here is the diagram you want to be familiar with. We're going to draw what we call a bell-shaped curve, symmetric curve. In the middle, very center, is your mean. This bell curve from end to end is 100%. Okay, the whole thing from here to the other end over here, okay, All of this is 100%. You need to know that. You cannot have more than 100% in statistics. This guy is even, okay, symmetric on both sides. So this left half, so from here on back, represents 50% of your data. And from this half all the way to the end is 50%. Okay, these are just important notes to know. Now, what the empirical rule is saying is that you're going to be given a mean, some number, and you're going to be given a standard deviation. Okay, we're going to be given sigma. Okay, we're going to be given a standard deviation. I'm going to say SD for standard deviation. What the rule says is if you take your mean and you add one standard deviation, so this will be your mean plus 1 sigma, and if you subtract that same value from the mean, so this will be your mean minus sigma, this interval contains 68% of your data. Okay, that's always the case. So 68% is right here between these 2 points. If you added sigma once, you'll be here. If you add it again, okay, so we go over another space. So this would be your mean plus 2 sigmas. So 2 times, we added it twice. And we'll do the same thing on the left. We subtract it twice, so this would be your mean minus 2 sigmas. Okay, between these 2 points would rest 95% of your data. Okay, and that's always true. So if you go 1 on either side, between those 2 is 68. If you go 2 on either side, between those 2 numbers is 95. And then we go 1 more. So almost to the end, but not quite. Almost to the end. This would be your mean plus 3 sigmas. So we added 3 times. And we subtracted 3 times. Okay, if you're between these 2 points, okay, the proportion of your data, percentage of your data between these 2 numbers is 99.7. Okay, and that's always true. No matter what your mean is, no matter what your sigma is, if we know we're using the empirical rule, we know it's bell-shaped, then the following is true. 68 between 2 or 1 standard deviation, 95 between 2 standard deviations, and 99.7 between 3 standard deviations. Now, there's one more drawing of this that we want to do, because sometimes you might not necessarily go 1 and 1 or 2 and 2. You might go 1 over here and 2 over here, and they want to know what's the percentage now. And so I'm going to show you how to break down each one of these sections in the next drawing. Okay. So I'm going to do another bell-shaped curve. And remember that this guy is symmetric, even on both sides. Okay, so mean in the middle, I'm just going to put 1 sigma and 1 sigma. So you know that this middle piece right here is 68. So if you take 68 and you divide it in half, I'm just to do that math over here, 68 divided by 2, you would get 34. So what that's telling you is if you start in the middle and you go 1 standard deviation either left or right, both of these pieces represent 34%. Okay, this is very important to note. Now, if we go 2 standard deviations out, so positive 2 sigma and then negative 2 sigma. Between these 2 points is 95% of our data. Okay, so we want to know what these 2 pieces are. Now total, whole thing is 95%. We've already counted the middle 68. So we just need to find these 2 pieces. So what we need to do is we're going to take our 95%, subtract the 68% that we have already accounted for in the middle. That leaves us with 27%. So these two pieces total make up 27, not each of them being 27. So to find each of them individually, we have to divide this by 2. And that would leave us with 13.5%. So these next pieces, 13.5. All right, and then you go one more standard deviation out all the way almost to the end. 3 sigma negative. Between these 2 points, rest 99.7% of your data. And it's just an approximation, pretty close, but just an approximation. Now, again, we're going to do the same type of calculation. So the whole thing is 99.7, but we've already accounted for 95% of it, okay? So over here, I'm going to do 99.7 and subtract off 95. That leaves us with 4.7. And then that means that these two pieces total are 4.7. If you divide this in half, because each piece is equal, you would get 2.35%. So 2.35. Now, this is it for the empirical rule, but you still need to know the whole curve is 100%, and we're not quite at 100%. So the last bit that we're missing is 0.3%. 0.3 is the last piece that we're missing, and that 0.3 is split up again into 2 pieces, one on either side. So if you take this 0.3 and divide it by 2, you would get 0.15. And it's kind of like 30 divided by 2 is 15. So the last very teeny part of the curve is 0.15% to make up your 100%. 0.15. Now, if you add up all of these, you should get 50 because that's half. Same thing over here. If you add them all up, you get 100%. So keep these handy. I'm going to be referring back to them when we start using them and do our examples in Hawks. But this is the empirical rule. It is very important. You're going to be using this process to solve problems quite a bit in chapter 6 and beyond. So 6, 7, 8, we'll be using this quite a bit, but you're getting introduced to it now. So here's their drawing, okay, showing you empirical rule. They give you a couple problems applying it. I'm showing you a partial breakdown, which I'll give you a few examples. And then the last thing we're going to look at is Chebyshev's theorem. Okay, Chebyshev's theorem just states the proportion. So same thing, the part of data that lies between X amount of standard deviation, or K standard deviations, they use K, is at least 1 minus 1 over K squared, and K has to be bigger than 1. So this is just an under approximation. Empirical rule is a better, okay, but Chebyshev's theorem just gives you a rough estimate of a lower bound. So if K is 2 and K is 3, you have the following. 1 minus 1 over 2 squared, and 2 squared is 4. So 1 minus a 4, so basically 1 minus a quarter, leaves you with 75%. So when K is 2, this is always the case. And then when K is 3, 1 minus 1 over 3 squared is 8 over 9, and then 88.9. So this is Chebyshev's theorem. Mainly we're going to use it for 2 and 3. These numbers will not change. So just like the bell curve, 68, 95, and 99.7, Chebyshev's theorem is just giving you a rough estimate. So with the empirical rule, we know that within 2 standard deviations that we have 95%. Okay, Chebyshev's is just giving you a low ball estimate. It's saying, well, I know it has to be more than 75%. It's saying at least 75, which we know that's going to be true because the empirical rule tells us it's 95% approximately. And these two just kind of agree with each other. So if you do 3, it says at least, so 88.9% or more is within there. And when we do 3 here, we know that it's 99.7. So yes, that would be true. Okay, so that is the majority of what we're going to be doing in 3.2. So let's jump into Hawk.